Sonic, the heart of your system.
Hi and welcome back to a new video. About a year ago we were analyzing a 9900K CPU 40 nanometer plus I think it is from Intel in regard of taking a look at a single individual transistor. We were doing that in cooperation with the University of Berlin. If you missed that, you can find the links in the description down below. Now Tescan, a manufacturer for scanning electron microscope, contacted me and said or asked if I would be interested in doing a cooperation and doing some more videos in this regard. And absolutely, this will be very interesting because back then it took a lot of preparation working with the University of Berlin. That was also the reason why back then we could only do it with the 9900K, even though 7 nanometer TSMC AMD was already out. But we didn't have the time to repeat it with TSMC 7 nanometer. By the way, Chic is doing much better. Here I have a 3950X, here we have a 10900K. We are going to drive to Dortmund, which is about 500 kilometers from me, and there we're going to compare and analyze AMD aka TSMC 7 nanometer versus the 10900K 40 nanometer plus or however it is called. First step is that I will have to disassemble the CPUs, take off the dies, remove the residues from the underfill and all those stuff, and then going to see how things go at Tescan. Well, yeah, 400 kilometers to go. You can see it's 10:30 in the evening. I've been sitting here for like an hour and nothing is moving because it seems to be like an accident. That is going to be a very long night. Yep, today is a great ride. Pressure sensor in the tire is telling me that I'm running low on pressure. Let's check. It's a little too less, like 0.3 bar. Alright, only took about 5 hours to drive to Dortmund, and now you can see I'm at Tescan. And we're just taking a quick look at some of those SEMs, and then after checking out those smaller ones we will head over to a different room where we're going to check out the big one, which eventually will analyze our CPUs. And that is the first SEM which we will look at. It's the Tescan Vega, same name as one of the AMD GPUs, and that is a basic one and also makes it a little bit easier to understand how those things work. It's a tungsten-based SEM, and the tungsten, well, the electron source is sitting on top right here, and then the electrons will be emitted down to the table right here on the bottom, where it's scanning the surface, and then you have a detector sitting inside which will allow us to take a look at the structure of the material. And on the side we have something that is called EDX, and this thing which looks like a cannon allows us to also detect what kind of materials are used inside. And if you just look at the table right here, the shiny thing in the center should be a nickel-based okay, it's a super material. Let's check out how this thing looks under the microscope and what it's made of. And that is, yeah, it's the cheapest or one of the cheaper SEMs they have, and you can also have it at home if you have the required money. It's about 100K. Could be a very interesting investment. You can magnify things up to 10,000 times, which is already quite a lot, but not enough for the CPUs we want to investigate further, because like 7 and 14 nanometer CPUs, they require a much higher resolution. Even the one in the back, that would work probably, but that is, I think it's like 200k euro. But yeah, we will need something even more expensive. Right now we are running an EDX scan of the surface of this chromium material, which we just saw on the table sitting down there. And the EDX, the way it works is you have all those electrons being shot down from the tungsten on top, and then it's hitting the surface of this chromium material, and once it hits the surface, it is removing some parts or some electrons from the atoms of this material, and then you have additional electrons joining the empty spaces, and in this process you have light which is emitted, and the EDX can scan this very specific wavelength and therefore can detect what kind of material is used. And while this is scanning, we're going to check out the other device. Okay, going over to Mira, the other device, which is a little bit bigger and also a little bit more expensive. We have something very interesting sitting inside there. It's a chameleon skin, or a fracture of a skin. It's this part right here, and to give you a scale, like how big this part is, on the bottom right here, you can see this is 1 millimeter, therefore, yeah, it's roughly the size of this part is 1 millimeter, therefore this should be like 3-4 millimeter wide, and currently magnification is 39 times. Very interesting structure, about 1000 times magnified. $20,000 times magnified. No, 50,000 times. 100,000 times, and it's going up to, yeah, almost, no, well, it's over 200,000 times magnified. And that is the structure of the skin of a chameleon, and it has those kind of holes inside the skin, something you would never be able to see with your bare eye. It's just possible to see this in the SEM. In the meantime, the part in the Vega SEM was, yeah, proceeded 100%. We have some interesting colors right here. What exactly can we see here?
So we have here an EDX mapping on a nickel-based superalloy. So actually what we are seeing here, the green colors is corresponding to nickel and to iron, and the pink colors are chromium atoms. So we have here the atomic distribution, the elemental distribution of iron, nickel and chromium, and we can see that the chromium is part of the carbides here, and the matrix is consisting of nickel. So we can overlay the map on the live SEM image. We can switch it off and on, and we can identify the faces, which we can see here in grayscale, actually with corresponding elements. And if we move the sample, we see that the corresponding map is also moving with the sample, so we can detect our region of interest in terms of elemental distribution.
That's Tom from Tescan, and we're currently at a point preparing the specimen.
We start with the silver blue, silver paste, which is conductive, slightly on the stub, aluminium stub, which is later going to be into the FIBSAM. Now we are going to get the chip. Get it onto the stub, slightly pressing so we get rid of air bubbles. Then we wait some minutes to dry, and ready we go.
On the right side, the 10900K, the bigger Intel CPU. Currently you can only see a metal layer on top. Both chips are lapped by hand, and on the Intel CPU you can just see one big metal layer on top. I'm not sure if you can see any kind of reflections, if you can see the cores. But on the AMD CPU on the left, I grinded a little bit more, and on the bottom left corner there's probably only silicon left, and on the top right which looks like some kind of residue. That is where we still have like the transistors underneath, and it's a little bit tilted, the grind, and I tried to make this especially so we can look at the layers from the top and then get a better or more interesting look from the top. Close up on the AMD CPU, you can guess that there is something underneath, but you cannot really see anything on the camera, but that will be definitely interesting. Yeah, meanwhile, we're still waiting on Windows. Thanks, Microsoft. Therefore, I think we have time to just take a closer look at the scanning electron microscope, and yeah, maybe you can give us a little overview of this thing.
Yeah, what's it gonna do? So here we have the core part of the whole FIB-SEM, the focused ion beam scanning electron microscope. It's the vacuum chamber. And in the vacuum chamber, later we will bring in our samples, which we have just prepared, and it will be put in the intersection point between the scanning electron microscope column, which generates our electrons, which we use for imaging, and the other intersection line basically comes from the ion beam, from the focused ion beam, FIB. And this shoots, in this case, with xenon ions. And the xenon ions can be used for imaging as well, rather low imaging compared, low resolution imaging compared to the SEM beam, but also, and this is the main point, for cutting off very specifically parts in our, in this case, chip, where we want to see at very distinctive locations where is what and how large is it. And that's the ion column which we're going to use. And then on top of that we have a gas injection system, which is specifically for this system. You don't basically need to have that, and this can be used for either deposition of materials as a protection layer. You can use it for selectively etching. You can use it for homogenizing your cut. You can use it for all kinds of stuff. You can be very versatile with that. That's the GIS, gas injection module system. Then we have several detectors on that system. One detector is, for example, this ion detector here, or we have here a secondary electron detector, which is here. This one looks pretty similar, but does detect something else, namely the secondary electrons. Here we have a detector which can be used to detect different types of materials, heavy materials or not so heavy materials, will show different contrasts. The detector which is just behind that will be a transmission type of detector, which we later then use when we created a so-called thing like TEM lamella, transmission electron type of lamella. So it will be a transmission detector, which we then later use for the high resolution nanoscaled imaging. That's basically roughly it. There are more details to it, but maybe that comes later.